like to tell you that many of the things that you read, that you see, or that you hear are not outright lies, but they're oftentimes not the whole truth. And in global climate change, the devil is certainly in the details. So yes, the talk title is Global Loop Warming, the New Climate Science that Changes Everything. At the Cato Center for the Study of Science, of course I'm interested in climate science, but what I began to discover about the scientific process while doing climate work led me to believe that other fields in science suffer from the same problems that climate science suffers from, owing in no small part to the way that we do science in the United States and in much of the world. We have a monopoly, actually a monopsony, provider for science funding for many scientific fields. In the case for climate science in the US, it's the federal government. And the issue has become highly political. That means that those who provide funding tend to, not in all cases, but in many cases that I can document, want a certain result. And also, because of the pressure to gain funding in the academy, in the United States, an assistant professor has to publish research costing, on the average, about $7.5 million in 5 years in order to be promoted to associate professor without term. We use the word tenure. So, who in climate science is going to generate $7.5 million of government funding by hypothesizing in a proposal that this may not be the problem that we think it is? Well, you see, in the United States, our proposals are reviewed by our peers. And our peers are all in the same situation. They know what works, and they know what threatens them. And so the result is preferential research in one direction, which is fine, I guess, except it creates a body of knowledge, the scientific literature, that is slanted in one direction. It's not done on purpose. It's not because people are being dishonest. It's because people are being people. With that, I will go into my discussion here. First of all, here's something that seems that I shouldn't have to say this, but the way that the global warming issue is often portrayed is there are people who believe it's the end of the world as we know it, and others who will say, oh, there is no such thing. And a lot of the ideologues on this issue will call those people deniers. Now, we all know what word comes before denier. It's kind of a dirty slur. But the fact of the matter is that there is an area in between those who say the world is coming to an end and those who say there's no such thing as a carbon dioxide greenhouse effect. And they believe, I think their synthesis is fairly accurate. They believe, does this thing walk? Oh, good. That's better. They believe, the evidence is very clear. Once I start to walk around, I'll speak too fast for the translator. But global warming is real. The temperature is about 8 0.2 of a degree C warmer than it was at the turn of the 20th century. This last year on this chart is very warm, 2015. I'll discuss that a little bit. That's because of an El Nino phenomenon in the Pacific Ocean. When an El Nino occurs, the normal trade winds, northeast trade winds and the southeast trade winds that blow into the Earth's thermal equator, either reverse or stop. And when that happens, cold water that normally comes up as the water is blown away from South America does not. It's called cold upwelling, and it's suppressed. And when that happens, the temperature peaks, just like it did in 1998, just like it did 1983. And then we'll see what happens after it peaks in a few minutes. So global warming is real. And I'm going to leave you with a saying. In the United States, it's very uncomfortable in the summer in the eastern United States. And what mothers will tell their children is, it's not the heat, it's the humidity. Well, I'd like to make a play on that. Well, in climate change, it's not the heat, it's the sensitivity. What do I mean by that? I mean, it has warmed up. Not all of the warming of the 20th century was due to human beings. Here, from 1910 to 1945, we had not put in enough carbon dioxide into the atmosphere to create that warming. If that warming were caused by carbon dioxide, this curve would be somewhere up on the ceiling by now. We wouldn't be chatting so friendly. Howsoever, it has warmed up. It will warm up, though there's some evidence that for some reason it stopped warming somewhere in the mid to late 1990s. And I was writing this talk yesterday on the train coming from Prague, and I realized that I had stumbled upon a piece of data that settles the debate, or at least will help to settle the debate as to whether the temperature warming has really stopped or is just continuing at a slightly lower rate. I'll show that to you in a little bit. But no, it's going to warm up. The question is, how sensitive is the temperature to a change in carbon dioxide? The term sensitivity is defined as the amount of global warming you get for doubling atmospheric carbon dioxide. For perspective, because of carbon dioxide and a few other, what we call greenhouse gases, we have effectively gone about halfway from the pre-industrial background concentration of 280 parts per million to an equivalent doubling of carbon dioxide in the atmosphere. So the question is not, does it warm? Not, will it warm? But how much will it warm? And for years, researchers have calculated probability distributions for certain amounts of warming. Let me show you an illustration from the 2007 report of the United Nations Intergovernmental Panel on Climate Change. It's going to look a little complicated, but it's really not. This is the climate sensitivity, the amount of warming you get for doubling carbon dioxide. And these are the probabilities of such sensitivity occurring, being realized, rather. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 different analyses. Now, what concerns people about this chart is what is called a fat tail. You notice the probability of large warmings are not vanishingly small. And that's the argument that many people use for extensive greenhouse gas emissions restrictions. That, well, yes, the mean sensitivity isn't that high, but look at what is called the fat tail. We have to have an insurance policy against the fat tail. The fat tail means that there's a reasonable probability of a high sensitivity. Well, you want to see how well those models are doing? This is not good. The red line is the average warming in all 102 of the United Nations Intergovernmental Panel on Climate Change's suite. They actually have 108, but 6 of them can't predict the upper air. So we use 102. This is the predicted temperature change from 1979 by the average of all the UN's models. This is not for the surface of the Earth. It is for what's called the lower troposphere. The bottom 20,000 feet, with most of the data centered around 10,000 feet, or 2.5 kilometers, bottom 5 kilometers of the atmosphere. The blue circles are 5-year running averages. These are 5-year averages of weather balloon data taken around the planet. Twice a day, at the same time, every day, weather balloons are released from weather stations. What's nice about the balloon data is the instruments are highly calibrated. Their accuracy is extremely high. Twice a day this happens at the same time. You can examine the data over a long period of time. There have been 4 different analyses of this data. The blue dots are the average of all 4. And the green squares are temperatures measured from orbiting satellites. That record also begins in 1979. The weather balloon data goes back to 1957, and that's going to become instrumental in about a few minutes, because you're going to see in about 5 minutes the day that I lost my faith in the, what's the word I'm looking for? The day I lost my faith in the purity of climate science. So, this is the surface temperature. This is different. But you can see, oh, by the way, why did the... Any of you wear graded lenses? Do any of you have what's called a bifocal graded lens? You can't see down. That happens about once every 3 days. Okay, be careful. We're asking the question, why does the climate model seem to be pretty good for the first 20 years or so? That's because these models start in 1995, and they're run backwards to whatever year you want to run them backwards to, and 2 things happened here. This is Mount El Chichon, a large stratovolcano. This is Mount Pinatubo. There were 4 stratovolcanoes in the 20th century, and they cooled the lower atmosphere. And so they were put into the computer model. And it's not a major feat then to reproduce the observed curve. But you can see it getting away, which it's doing. Now, if you're really, really careful, you're going to look at this chart and say, Michaels, your data ends in 2014. And you just showed that 2015 is really, really hot. Why did you not put 2014 in there, or 2015 in there? Because the El Nino spike of 2015 and early 16 is beginning to degenerate. The next data set, the next year, it will logically be shown that would not have the massive El Nino impact would be 2017. And I will show you. I don't know, have any of you read that global temperatures are dropping rapidly? Well, they are. Now, the notion that these computer models are not getting it right isn't new, believe it or not. This is from the United Nations report in 1995. And I won't read the whole thing, I'll tell you what it says. It says, when we put carbon dioxide into a climate model, and carbon dioxide only is what changes, the models predict too much warming. Unless, listen carefully, a lower climate sensitivity is used. In other words, the models are generating a sensitivity that's too high if they just have carbon dioxide. This has actually been known since the mid-1980s. And then the next sentence says, there's growing evidence that increases in sulfate aerosols are partially counteracting the warming. Sulfate aerosol is what comes out of a coal-fired power plant. It's what comes out of a burning forest. And the idea is that the sulfates reflect away solar radiation and therefore cool the surface, countering the warming from carbon dioxide. That's a really testable theory because what it says, remember, if you've ever been to the southern hemisphere, you fly into the southern hemisphere, you know when you get into the southern hemisphere because the sky is brilliantly blue. The atmosphere is really clean. Why? Because there are hardly any people in the southern hemisphere. There's not very much land. And what land there is, consider Australia, doesn't have a lot of things to burn because not much grows there. So the southern hemisphere is very clean. The implications of this are that because the southern hemisphere is completely lacks these sulfates, yet carbon dioxide diffuses around the planet, that the southern hemisphere should be warming more rapidly than the northern hemisphere. And indeed, I want to back up for a second. The acceptance of the low sensitivity paradigm, the idea that sensitivity is too estimated too highly, takes a lot of time. A book was written in 1962 by Thomas Kuhn. It's a classic. It's called The Structure of Scientific Revolutions. Any student of science reads this very early on in their career. And he wrote, in science, novelty emerges only with difficulty, manifested by resistance against a background provided by expectation. Listen to this. Initially, only the anticipated and the usual are experienced, even under circumstances where anomaly is later detected. What he's saying is that scientists will defend their point of view, basically to their death. Scientists die, like the cowboys at the OK Corral who died with their boots on. Scientists die with their paradigms on. So, what we said was the sulfate hypothesis would predict that warming should be greater in the southern hemisphere, maybe away from the ocean, in the free atmosphere, and in the northern hemisphere. And this paper was published 1 week before the third conference of the parties to the United Nations Framework Convention on Climate Change. That was a meeting held in Geneva in 1996 that was supposed to set the ground for the Kyoto Protocol on global warming, which was the first true international agreement on global warming, set the ground for the next year. I don't think it's an accident that this paper came out when it did in Nature magazine, which is the highest impact magazine in the world. And I want to read you the abstract, because this was when I lost my faith. The observed patterns of temperature change in the free atmosphere from 1963 to 1987 are similar to those predicted by state-of-the-art climate models, incorporating combinations of changes in carbon dioxide, anthropogenic, that's a big word, human-caused, sulfate aerosols, and some other little things. So, what Centra and his friends are saying is that we are modeling the evolution of atmospheric temperature in 3 dimensions, and we're doing a really, really good job, just in time for the meeting that sets up the Kyoto Protocol. And indeed, when I read this, it was the 4th of July. I was talking with a friend of mine on the phone by the name of Robert Ball. I mean, he was the author, the second author of the first book. And I said, Balling, there's something wrong here. I can't quite put my finger on it, but I think it has to do with 2 numbers. And he said, what do you mean? I said, 1963. In 1962, the 3rd of the 4 stratovolcanoes of the 20th century went off. It's Mount Agung in Indonesia, and it dropped the temperature. So that means this study is starting at a cold spot in the temperature record. The weather balloons, as I said earlier, start in 1957. Why did this paper not start in 1957? And may I remind you that this paper comes out in the summer of 1996. Where's the data from 1988 through 1995? It might have been available only through 94 at that time, but where's the data after 1988? Everybody knows, after 1987 rather. Everybody knows it's available, and guess what? You see this name? A.H. Oort. Where is he listing himself as from? If I got my things right, he's from Princeton. Oort was the guy who put together the weather balloon record. He knows it starts in 1957. He knows it ends in 1995 at that point in time. Well, here's how well the model worked from 1963 through 1987, the subject of this paper. Okay, bear with me. North Pole, equator, South Pole, 5,000 feet, 1.8 kilometers, 50,000, closer to, what's 60,000 feet in kilometers? About 21 kilometers. Okay? So again, North Pole, equator, South Pole, 2 kilometers, 21 kilometers. And this is what was observed, the observed temperature trend during this period. Now, do you remember that I said that sulfate was interfering with the warming because there are no sulfates in the southern hemisphere, that the southern hemisphere would be warming with respect to the northern hemisphere? And look, there it is in the real world. In the northern hemisphere, less warming. This is the computer model. This is pretty darn good. This is as good as it gets. And all the power in this comparison comes from this big hot spot in the southern hemisphere, off the surface. Here's how you lose your faith. let's start the data in 1957, where they actually begin. Let's end it in 1995. Here's what this hotspot did from 1963 through 1987. And here's what it did for all the data. You lose your faith too. And then you wonder what you should do next. Well, the senior author of this paper wasn't very happy. This was published in Nature magazine, also, by the way. Here's one of the famous stolen emails from the University of East Anglia. Next time I see Pat Michaels at a scientific meeting, I'll be tempted to beat the crap out of him. Very tempted. So not only have I lost my faith, but somebody's losing their manners. Now, let's talk about today. This is the satellite record. And I want to show you why I stopped that comparison in 2014. Here is the big El Nino of 1998. It's probably one of the biggest ones we have ever measured. I'm sure there were a couple bigger ones in the late 19th century. But here's the huge temperature spike when the cold water off of South America is kept underneath the surface. And when it hits its peak and the cold water comes back, remember, this stuff is just sitting down there and building up, building up. And when the trade winds come back and move the warm water off the coast of South America, the temperature drops with a vengeance. And it drops fast, and it actually will tend to drop to below where it was before the El Nino. Well, take a close look at the 2015-16 El Nino. May, April, March, February 2016, going down dramatically. When we get out to about here, 10, that temperature curve is probably going to look just like that. By the way, do you see any warming? This is the satellite record for the lower troposphere. No, don't see any. However, if you take a look at the overall record, which extends back to 1979, you will. To give you an idea of what's about to happen, this is early March, and this is the end of this March. This is the cold water underneath the surface of the ocean. You can see it just getting ready to come up. So the news, the reason you're hearing so much news about global warming this, global warming that, is the people who are writing those stories know what's about to happen. Here, there's another record. This is a good one. You can actually get global temperatures not from satellites, not from weather balloons, but from surface weather stations within about 24 hours of when they're taken. So this one is updated, let's see, this is 14th of June of this year, very recent. The blue is the northern hemisphere. There's the El Nino peak in the north, there's the El Nino peak in the south. Has anybody read that the southern half of our Earth's surface temperature is now below its long-term average? It is. By the way, NCEP, National Center for Environmental something or other, the U.S. federal government group of people. Now, here's the satellite record as a whole. This is an older image. This one only goes to April, so it's March. It's missing. It's missing the last 2 months. But you can see there is a warming in the record. It just tends to stop somewhere around here. Nonetheless, there is a significant trend in it. It's about 0.14 degrees Celsius per decade, and it's there. Now, it's basic global warming science. This is where you realize that this problem is actually, and from a scientific point of view, we actually have a very simple solution. We may be able to correct the models just with a pencil and a ruler. Carbon dioxide goes in the atmosphere as a low-order exponent. It's like compound interest of about 1%, which is about what you get on your dollar since 2008, unless you're in Germany, where it's going to be negative pretty soon. It's not funny, it's real. So it goes up as a low-order exponent. But the response of temperature to carbon dioxide has been known from laboratory studies for a long time in a laboratory. That's quite a bit different than a complicated Earth. But the response of temperature to carbon dioxide is a logarithm. Function that looks like this. For every change in carbon dioxide of the same amount, you get a little bit less warming. It never goes flat, never gets flat. But really, one of the things a climate model does is it does what you did in pre-calculus. It adds up mathematical functions. And in the roughest sense, if you add up a low-order exponent and a proper logarithm, you get a straight line. So, do the computer models predict straight line warmings? As they say out west, darn tootin', they do. Each piece of colored spaghetti is a computer model. This is from the 2007 IPCC report. They didn't make such a nice picture for the succeeding ones. Things really haven't changed. The dotted line is the average of all the UN's climate models from that report. And I hope I can convince you that that's a straight line, or pretty close to straight. So, take a look at the temperature history since the second warming of the 20th century started in 1976. This has 2015 in it, even with the El Nino, here's the 1998 El Nino, here's the 1983 El Nino. Even with the El Nino spike at the end of the record, it's very clear that the warming is a straight line. So, we did something right. We got the mathematical form of the warming right, but we missed the magnitude. Now, I used to teach weather forecasting at the University of Virginia. I had several students who were much better than I was. And what you tell students, there are about 7 or 8 global or regional forecast models applicable to North America. What do you tell students to do when one computer model says, it's going to snow a half a meter in Washington, D.C. That'll fix them. And then the other model says, no, it's going to rain. It's going to turn to rain. You tell the student, look out the window. Literally. What I mean by that, in this case, is you can look out the climate window. And you can tell which of these models is closest to reality. And it is the yellow one. So maybe that's what we ought to be looking at. Now, there has come a great debate. This temperature record was recently altered in response to a federal employee who, just in time for the Paris conference, published a paper in Science magazine that has been more severely criticized than any non-retracted paper I have ever seen in Science magazine. Claims to have gotten rid of what's called the pause. He said the warming is now significant and then in parentheses, it says P equals 0.10. That's not significant. That's not the normal rules of science. There was sure a lot of pressure to get this thing into print. And what he did was he took out the satellite sensed sea surface temperature data and then relied upon the remaining measurements, many of which come from ships, onboard ships. There are intake tubes where the ships take in cooling water. You're raising your eyebrows because you know how hot that ship gets in the sun. The temperatures, there are problems with these intake tube temperatures. And then it also relies upon a new and growing set of buoys. Buoys that have calibrated instrumentation on them and indeed get the temperature accurate. But what he did was he raised every buoy temperature by 0.12 degrees Celsius. Why? So it would match the shipboard data. Now, think about it. We're putting out more and more buoys whose data is being raised by 0.12 of a degree for every reading. I can guarantee you that that will put some warming in a heretofore non-warming record. But here's the killer. This happened on the train, halfway between Prague and here. By the way, I love your two countries. Can I call them your two countries? Or what? Anyway. My real last name is Mahalchik. My father changed it because people couldn't pronounce it. And unfortunately, he spoke Polish, but he never taught me. Anyway, here's what I have discovered. Okay, here's something we all know. Carbon dioxide is a molecule shaped like this. And the sun radiates onto the earth. High energy radiation, ultraviolet radiation, gives us sunburn, like that. And the earth radiates out at a lower energy. Nobody gets earth burn. The earth has to radiate out the radiation that comes in, otherwise it will heat up and heat up and heat up and heat up. So the earth's at thermal equilibrium. Now the sun changes its output a little bit, but not that much. And the carbon dioxide molecule resonates with the piece of energy that comes from the surface of the earth. And when infrared radiation, being warming radiation, and when the carbon dioxide molecule surrenders the piece of energy called a photon, it can either go back up, continue to go up, go out to space, maybe hit another CO2 molecule, or it will go down. And that means that the lower portion of the atmosphere is warmed by carbon dioxide. But we're not adding energy to the system as a whole, to the Earth, atmosphere, ocean system. We're not adding any energy. The only way you would do that is if the sun got hotter, or if it became less cloudy. It's a very large phenomenon like that. So anyway, so that means that the lower atmosphere will warm, but the stratosphere above the lower atmosphere must cool in order to maintain radiational equilibrium. Why don't you start by looking at the left-hand side of the image I'm about to show you. I'm going to be like a politician watching this stand in front of what I don't want you to see. This record begins in 1979, and you can see here's the volcano warms the stratosphere that cools the surface. Here is the general cooling of the stratosphere. And when we get to this, has the warming stopped in the surface era of the mid to late 1990s, what happens? The stratosphere stopped cooling. This proves that the pause is real. And I'm going to write this up and send it to either Science or Nature. Probably won't have time until after I get married. on July 23rd in Scotland. Some people have been arguing for low sensitivity for quite some time. This paper was published in 2001, and it argued for around 1.6 degrees. And then in 2011, whoops, a large number, oh, shoot, I didn't put that in there. I took the slide. Pardon me. In 2011, a larger number of papers began to be published, and there are now about 50 separate experiments published in the scientific literature showing sensitivity averaging about 2 degrees Celsius, where the United Nations computer models are at 3.2 degrees Celsius. So it's starting to come into line. I'm not going to wait. Well, should I do this? Yeah, I have to. This very busy graph I presented in 2014. It is a comparison of all the UN's climate models to reality. And what I did was, there are 104, I think, or something like that, that we used here. They predict different amounts of warming. And the amount of warming they predicted has a normal distribution about the average amount of warming predicted by all the other models. So you can look at the 95th percentile of model warming, you can look at the 5th percentile of model warming, or the 2.5 percentile. The black dots are the average warming predicted for the last 10 years, the last 11 years, the last 12 years, the last 20 years, on out to the last 61 years, meaning somewhere around 1950. The average warming predicted by all the models. That's the black dot. The colored dots are reality. Where the colored dots are green, they have predicted warming and observed warming are within the statistical limits of each other. Where they're yellow, the models fail at the 5% confidence level. When they're red, they fail at the 2.5% confidence level. This is a failure. So now, more pieces of evidence. The sulfate, these are models driven by sulfate and carbon dioxide. They don't work. The reason they don't work is because the sulfate effect is too large. If the sulfate effect were real, this is a different representation of something you've seen earlier. The red is the northern hemisphere. The blue is the southern hemisphere. The last data point should be disregarded. This is the wrong image. That's the average through the first 4 months of 2016. That's going down, so don't worry about the last data point. That's going to drop below. Probably drop below this one. Anyway, the clean southern hemisphere, if the northern hemisphere warmed up this much with sulfates in the air, the clean southern hemisphere should have gone through the roof back then. It didn't. If the sulfate hypothesis is working, the northern hemisphere should be warming less than the southern hemisphere. You saw that from the paper that I showed you that I lost my faith over. So that's not happening. Unless we have overestimated the cooling from sulfate aerosol. And that appears to be the case. You can actually take the observed temperatures and the known emissions of sulfate aerosol and tune them to see what the frequency distribution of equilibrium warming will actually be with a more realistic sulfate effect. This was done by Nick Lewis and Judy Curry. Judy Curry from Georgia Tech. She began speaking out on climate change about 5 years ago. Funny how she changed her mind when she stopped applying for government funding. And now, of course, everybody hates her. The equilibrium sensitivity here is about 1.4 degrees or so. These are for 4 different experiments done. But notice the most important part. The fat tail is gone. The fat tail is gone. So, insurance policy is needed. Here's the slide I was looking for. These are the ones since 2011. I don't know how this got this. Every talk I screw something up. I just screwed this up. These are all 50 bajillion experiments. The latest one here is Bates in 2016. He's got about a 1.25 degree sensitivity. These are the 95% confidence limits for the sensitivities. The fat tails are dead. Now, I'm going to close. I could go on and on, but I'm going to close with a subject that would be brought up in discussion in the United States and college. And it will be, but James Hansen, that's this guy right here, Jimbo Hansen, says that all the ice could fall off of Greenland in 100 years. If that's true, the sea level would rise 23 feet, 7 meters. It would rise 7 meters. And in a court case that I was on with him, so this is under oath, it is my opinion that 2 degrees, 3 degrees C global warming would likely cause a sea level rise of at least 6 meters within a century, and he later says that could happen this century. Okay, so that is the scare story, the remaining scare story from global warming. Will it warm up enough to have Greenland shed its ice? I don't want that to happen. Here's the Greenland story. Have any of you ever flown over Greenland or been to Greenland? I go to the real hot spots for vacation. 3 years ago I went to Greenland. Have any of you ever been to Iceland? Iceland's very cool too. Iceland's much more fun. Anyway, if you fly over Greenland, what you see in the middle of the summer is there's water all over the surface of it as you get closer to the coast. That's because it goes below freezing every summer in coastal Greenland and fairly far inland. And so the idea is that there'll be much more water. As it warms up, the water will flow down into the bottom of the ice cap, lubricate the ice cap, and it will fall off of Greenland. That neglects one critical piece of information, which is the reason glaciers are glaciers. And the reason glaciers flow is because the pressure underneath them is so high that there's liquid water. But let's have this hypothesis and worry about it. So ice flow enhanced by meltwater. Instead of 2 inches of sea level rise by 2100 from Greenland, we get 20 feet. And is the warming there unprecedented? Well, one thing we know, if you dig down in the tundra, in the northern end of the boreal forest, you'll find trees. And the trees can be carbon dated because they're preserved in peat. It's very acidic soil. So they're preserved to be carbon dated by usins. And what you find is in northern Eurasia, and probably in northern North America too, there's no reason why it wouldn't go along with it. What is now the boreal forest, the Northwoods, extended all the way into the Arctic Ocean. Not just into the Arctic Ocean, but onto islands in the Arctic that are completely barren, like Wrangel Island and Nova Zemlya, where the Soviet Union blew off the Tsar bomb. So we know how warm it has to be for the boreal forest to live. The July temperatures would have to be 6 to 7 degrees Celsius warmer than the 20th century July temperature for that to happen. And so the ice survived at least some period that was quite warm, And that also means that the Arctic Ocean was ice-free at the end of summer for a large portion of those years. Considering these lines of evidence, a picture evolved suggesting the Arctic sea ice cover was strongly reduced during most of the early period after the end of the last ice age. There appears to have been periods of ice-free summers in large parts of the Arctic Ocean. Geological Survey of Norway, they have it at 6,000 to 7,000 years ago, suggesting the Arctic Ocean was periodically ice-free. Tell that at your next Christmas party where your environmentally oriented friend starts crying about the polar bear. Because the polar bear survived ice-free Arctic Ocean for hundreds of years or so. But what about Greenland? This is my favorite part. As you know, we did not just experience one ice age. I was alive during the ice age. Some of you it might have been also. But there were 4 major ice advances. And at the end of the second last one, known in America as the Illinoisan glaciation or the Sangamon, I don't know what the name of it is in Europe, but the beginning of that interglacial was much warmer than the beginning of the current one, which was still warm enough to push the boreal forest into the Arctic Ocean, which was smaller, by the way, because there was more land ice. So there was more land. So, 118,000 years ago, there's a woman, not a woman 118,000 years ago, a woman from University of Copenhagen who has a big research team. She's called Dorothy Beltensen. And she published a paper that, boy, I didn't hear about it on the news. You didn't hear about it on the news. You're going to hear about it for the first time here. Everybody, this period of warmth that was 6,000 years long at the beginning of the last interglacial, not this one, was thought to be about 2 to 3 degrees C warmer. And she drilled an ice core, got to the bottom of the Greenland ice, no small feat, and darn it, if you can count the years because of the melting. So you know how old the ice is. And she got down, and when she got to the rock, it was about 125, 130,000 years. So she had cut through what's called the Eemian, the warm period. In each year's worth of ice, there are air bubbles. And the ratio of the uncommon isotope of oxygen 18, to the common one, oxygen 16, varies with the temperature at which that snow condensed. So it's a very good thermometer. And lo and behold, she found it wasn't 2 degrees warmer, it was 6 to 8 for 6,000 years. Another isotope in her core could be used to estimate the height, the altitude of the ice. Right now, the thickest part of the Greenland ice cap is about 3 kilometers, where she was taking her core was closer to 2 kilometers. It's about 2.25 kilometers. But she could, I think it's a beryllium isotope, I may be wrong about that, will tell you the altitude at which the ice was. And it turns out, after the 6,000 warm years, the height of the ice was, there's a big error range on this one, between 400 feet above, or to 1,000 feet below. In other words, 125 meters above to about 300 and some odd meters below where it is now. And she calculated, because she was from the cold spot in Greenland, she was in northwestern Greenland, that around the coastal areas there would have been more melt. And her calculations showed that the amount of ice that fell off of Greenland, came off of Greenland for 6,000 years was about 27% of the ice. Now, never throw up an equation in a talk. A little math, okay? Here's how much heat was unloaded onto the Greenland ice cap. 6 degrees Celsius for 6,000 summers. So the unit of heat would be warmth times time. 6,000 degree summers. That's the load of heat that went on the ice in the Bohemian 118, 120,000 years ago. Climate models, worst case, is 5 degrees C for 500 years. I don't think it will be 500 years, because we're going to change our energy structure as long as we don't destroy our economy in futile attempts to use technologies that don't work. I almost said a little bit too rapidly, I apologize. When I'm being smart, I speak fast. So 5 degrees C times 500 summers is 2,500 degree summers over the Greenland ice cap. That's all we can do. We can't push it above that. That's probably an overestimate. And it survived 36,000 degree summers. So, what does that tell you? Well, I'll tell you a story. I'll close with a story from a paper that was published a few years ago in Proceedings of the National Academy of Sciences. A woman from the State University of New York at Buffalo found a skeleton. And she sequenced the DNA in the mitochondria of the bone cells. And you know what kind of animal it was? It was a polar bear, and it was 125,000 years old. So the polar bear survived 6,000 years, 6 degrees C higher in the high Arctic. We can't even get to 1/10 of the heat load that occurred in the beginning of the end of the second last ice age. I could go on. I have some other interesting stuff, but I rightfully sense boredom. I'll leave you with one horror story, and that'll be it, while we're talking about the polar ice. We have satellites that measure the extent of ice in the high latitudes of in the Arctic Ocean. This is the polar sea ice extent. The satellite, LIGHT, the temperature sensing satellite, starts in 1979. It takes money to send up a satellite. And your agency has to sit in front of Congress with some skeptical congressman. Why should we build you your ice sensing satellite? Well, Senator, the ice has been growing rapidly up there, and we're afraid of a new ice age. That was the reasoning for this satellite. In fact, the late 1970s, when this satellite was launched, were the coldest period in the Arctic summers, all the way back to the mid-1920s. And there was some ice age fear. I have to say, I couldn't warm up to that one either. But, so this ice has expanded beyond its norm when the satellite starts up. Our friends at the United Nations Intergovernmental Panel on Climate Change write that about half the ice loss from the Arctic is because, in this record, is because it started out abnormally high. So about 50% of it's some internal oscillation, and probably 50% of it has to do with us warming up the air in the Arctic. Very interesting. It drops quite rapidly. I haven't read the news story that it levels off about 10 years ago, but it gets noisier. And that's because the ice is thinner, so it melts faster. This year, there's a big heat load on the ice this year, only one teensy-weensy, itsy-bitsy problem. The satellite sensor broke 3 months ago. And so it will be measured with a different satellite that's not directly comparable to this. So you will hear horror stories this summer, but just remember that the microwave starting satellite broke. There'll be another one put up pretty soon if we don't run out of money. But we're working on that. We have an election coming, did you know that? We have the two most unpopular politicians in the United States running against each other. What a great story. Anyway, just for the heck of it, once upon a time, there was a satellite picture of the Earth in the Washington Post. And the southern hemisphere was at the top. Here's the ball. Al Gore commented on it. He said, oh, they got the Earth upside down. No, not quite. But there is another hemisphere, half a sphere. Let's take a look at the southern hemisphere's ice extent, measured by the same satellite. See, the satellite is in polar orbit, and so it goes over the northern hemisphere, North Pole, and then about 2.5 hours later, it falls around the southern hemisphere, takes its readings there, and then goes back to the north and the south. And so here are the readings for the southern hemisphere. And yes, your eyes do not deceive. There is a statistically significant increase in southern hemisphere ice extent. Now, a model is not a truth. A model is a hypothesis. The weather forecasting model is a hypothesis about what's going to happen in 2 days, verified or rejected by what happens in 2 days. The computer model is a hypothesis about what should happen to Arctic ice, or what should happen to Antarctic ice. And I will close, because everybody wants me to close, with this image. Here is the Antarctic ice in reality, and here are the computer forecasts for Antarctic ice. Now, one of the major controlling factors of this planet, the temperature of the planet, is how much radiation is not absorbed. White surfaces don't absorb radiation. That's why people don't wear black in Saudi Arabia, because you will bake. In black, anything will actually do not so badly in white. So if you've got all the whiteness change in the planet, wrong sign, maybe that's another reason why the sensitivity of temperature change to carbon dioxide has been so dramatically overestimated. I want to thank you. I know listening to a translation is very hard, especially from a person who thinks he's funny. So the humor usually doesn't translate very well. So thank you very much.